like whatever you like to do instead of the very small things we can do during the pandemic. Okay, so today I want to talk about conditional probability and Bayes' theorem and do some examples, and we may have a little session for you to do some things in a breakout room if I can, depending on how many questions we have. Let me share my screen and we'll go over to the document camera and do some more probability, more mathematics. Let's see. All right. So let me make the long trek to the other end of my office here. And we'll continue. All right, so please let me know if you can see and hear me, and if you can also see the document from the document camera.
Yes.
Good, terrific. Okay, so this is a little recap of what we did last time and what we'll be using in the future. So this is why it says recall. So what will we need today? So the context of this is that there's sometimes in my training when I was really pleasantly shocked by how well you could calculate for some of these abstract things we were learning. And one example from physics, as I mentioned, is quantum mechanics. It's really remarkably accurate, and you can calculate all sorts of things. And of course, that does relate to probability, but in our sense, probability is incredibly useful for calculating things. You can do all sorts of marvelous sorts of computations, even on paper with a computer. And we want to get you at the point you can use that and use it in your programs. So remember, we started with the definition of conditional probability. And this was basically, we could write it in this nice compact form because we had axioms for probability here. In other words, we axiomatized probability, or we grounded the meaning of probability using set theory and functions, so you really know what you're doing, which is necessary. And one of the things we stated but did not prove was the law of total probability, LOTP, which is roughly stated as follows. And we used it a little bit in some examples. So this is a way of calculating probabilities that is extremely useful, particularly in Bayes' rule. And I want to take this a little further. And if we have time at the end, we'll give you some hints on how you would prove that, or maybe even ask you to prove it. Let's see how time goes for that. Okay, so with this in mind, let's kind of take our examples a little bit further and think some about probabilities again. And I want to go back to the example of birthdays and whether they're twins in the class, and giving you a little introduction into what's called Bayesian probability. So recall, and this is lecture 20, that we computed then the unconditional probability of a shared birthday. So the probability of a shared birthday, say in a class such of R's, is equal to something like 1 minus n times n minus 1, all the way down to n minus k plus 1 over n to the k. And I'll just sort of write that here. This is the unconditional probability of a shared birthday. Now, one of the things we would like to do is take into account conditional probabilities. And I gave you the anecdote of when I had two identical twins as TAs, Hunter Nisanoff and Tyler Nisanoff, and another time when we had two students that were twins, not identical, in the class. And that greatly changes your calculations about whether or not there'll be a shared birthday, because assuming that the birthdays weren't split over midnight, they had the same birthday. So if you know they're twins, then you know a lot about birthdays. Let's try to model that. Bayesian probability will be a nice way, but we can just get at it with conditional probability. Let's think about it. So imagine we have some events. Think back to law of total probability, which I have right above here. Suppose I have an event such as F1, and that F1 is the event the class contains twins. And we have F2, which is simply equal to the complement of F1. Remember, that's defined as the entire outcome space minus F1. And this is the probability that there are no twins in the class. And these are mutually exclusive. Either they're twins or they're not. And suppose we have some other event A. I'm using the same terminology as the law of total probability. A is the event, which is there are two students with same birthday in the class. So some things to note here. The conditional probability of A given F1 is 1. I'm not going to consider the case of split over midnight. So if they're twins, then you're guaranteed to have a shared birthday. And this beast here is actually the probability of A given F2. So this is the unconditional probability, so there are no twins in the class. Well, pretty cool, right? So now we can use the law of total probability to put these things together. There might be twins, there might not be twins. So we can say the probability of event A, namely of a shared birthday, let's just use the law of total probability as written out here. It's going to be equal to the probability of A given F1 times the frequency of F1 plus the probability of A given F2 times the frequency of F2. Now we can put in some numbers here to do some calculations. Let's look at 3 different cases, which are really all kind of the same case. So case 1, we can look at the probability. Suppose we know that they're twins in the class. So this is a nice case here. Then this reduces to 1 times 1 plus 0 times some probability of unconditional twins, which is 1. So as you might expect, the probability of there being a shared birthday works out to be 1 if you know that they're twins. On the other hand, if you know that there aren't twins, this is case 2, the probability of the twin event is 0, then you get the probabilities are 1 times 0 plus 1 times this quantity here, which we calculated last time. So it reduces to the case we had before. And more generally, if you had some reason to have an estimate of what is the frequency or probability of twins, the general case, case 3, where you might have the probability of there being twins is some other parameter, alpha, which of course is between 0 and 1, then we have this very general case of the probability of A given F1 times alpha plus the probability of A given F2 times 1 minus alpha. This is just alpha, 1 times alpha, plus our probability from before, probability of A times F2, 1 minus alpha. So if you had some a priori estimate beforehand of how likely you thought it was there were twins in the class, you could use this general formula, which of course has the other 2 as subcases. So this is yes. Question?
Could you move the page up a little?
Oh, yes, of course I can. Thank you so much. I got so excited. Is that better?
Yes, thank you.
Yes, sorry about that. So this is a very simple example, but I just wanted to say that this is a case where I wanted to illustrate the strengths and weaknesses of drawing diagrams to illustrate these cases. So with the law of total probability, you might have been tempted to set this up in the following way, which is a good idea. So you might have said, look, I have this space of outcomes here, like this. And I have 2 possible outcomes. I have outcome F1, event F1, which is twins, and I have event 2, which is no twins, like this. And then I have some arbitrary other event A, which is the probability of a shared birthday. You might set it up like this, mimicking my diagram from before. And of course, this is a perfectly good way to visualize the law of total probability. We have some events F1 and F2. They form a partition of the space, namely their union is equal to the space, and they're pairwise disjoint, and the event A is completely arbitrary. And this does help you visualize the problem. But one question you can ask in this particular case here is, what is the set event, if you will, F1 minus A? So what is this set equal to? Does anyone have any thoughts? Like, what does it mean semantically, but also what does it look like in the diagram? Remember, all events are set, so I can do set operations on them to get a new event, but I want to know what this event would mean. Any ideas?
Is it empty because a class can't contain
So let's go back to the definitions. So F1 is the event the class contains twins, and A is the event there exist two students with the same birthday. So what are we asking when we construct the event F1 and not A, or F1 minus A?
Is it the probability that the class contains twins, but no two students share a birthday?
Yeah, that's exactly right. So it's kind of a weird case, right? And probably that shouldn't be as big as this region here if we're drawing this to scale. So I guess this could happen if you're split over midnight, but probably most people think of twins being born on the same day. So probably a better diagram would be something like this, in my opinion, where we had A look like this. So this is our set A like that. Our entire set, I'll draw the A a little bit better so you can see it. And our set omega is this thing here. This is our set omega. And this guy here is F1, this guy here is F2. Right, draw a line down here. So really, in most interpretations of this problem, this is in fact equal to the empty set. We don't really think of twins having different birthdays, or at least it's very small probability. So one of the things about drawing these general diagrams and why we don't consider proof by diagram to be a proof technique is that you can get obviously very confused. There might not be any points in F minus A because we don't really have twins that don't share a birthday. And so you kind of want this to squeeze that out. So diagrams very useful, help you visualize, but they're not proofs. And this is one example of how it could lead you astray. Didn't lead us astray, but it might do that. Okay. So a simple example of the law of total probability, and we've integrated our notion of conditional probability into our birthday example using a simple example of twins. Okay. Now this leads us to the doorstep of what's called Bayesian probability, which I will talk about and then use. So a little bit of math and then we'll apply it in an example. I'll put these aside because I'll just want to come back to these and maybe we'll prove the law of total probability later. Sometimes statistics, the law of total probability is called Bayes' first theorem. And this Bayes formula I'm about to show you and prove is sometimes called Bayes' second theorem or second formula. And it's very important. So I'll just call this Bayes' second formula. And this is the basis of all statistical inference. So it's actually vital for all of statistics, but particularly for machine learning, parameter estimation, engineering, many different areas where we want to make inferences about statistics. Now, we're going to use the same terminology here as we did the law of total probability, but I want to give you some terminology that's frequently used in the statistics community. It's sort of a secondary, not secondary terminology, it's a good terminology so you can know what it means. Let me write this down. And I'll use the same notation I had before. So in our mind, Fj is an event. But in the Bayesian framework, it's often called a hypothesis. Now, the probability of Fj is often called Fj's prior probability. And the probability of Fj given an event A is called the posterior probability. Now, generally in mathematics, memorization doesn't get you very far, but in order to communicate with the machine learning, AI, and statistics folks, these terms are simply worth memorizing. We're not going to test you on these terminology a priori. This isn't a terminology class, but I recommend being able to go back facilely between the world of probability and the world of statistics. So these are what these things are called. Let's do the theorem and then we'll do an example. So Bayes' second formula, specifically Bayes' theorem, is often stated like this, and we'll prove it. So probability of Fj given A is equal to the probability of Fj times the probability of A given Fj over the probability of A. And of course, you could also say this in words by noting this is called the posterior probability, this is called the prior probability, and so forth. Okay. Now, how can we prove such a thing? Like, why should such a thing even be true? So what I'm going to do is I'm going to basically, whenever things get tough, I'm going to run to set theory, because set theory is just something we know a lot about. We can manipulate it, we can do things. So I'm just going to write down what we have here using the definitions of set theory and then try to manipulate them. So what I'll do is I'll write down the probability of Fj given A. And instead of writing that down using our formula, which is a perfectly good formula, if you have basically what I want to do here is I want to expand that using our definition of conditional probability in some sense. I basically want to just write it down like this. So I have this, I want to go back to the language of set theory. So let me just write this down. I'm going to sort of do this in really two different ways. So I'll write this down, and this is just by definition. This is the probability of Fj intersect A divided by the probability of A. And while we're at it, let's write down the probability of A given Fj. And just using the definition, that's equal to the probability of Fj intersect A divided by the probability of A. Oh, sorry, probability of Fj. So the only difference here is in the denominator, right? I'll write that out again so it'll be cleaner. Okay. Okay, so we've basically just expanded the definitions here we have for conditional probability using our definition using set theory. So now what I want to do is I want to basically solve for this, right, using the second equation, just by multiplying by the denominator. So I'm going to write the probability of Fj intersect A. Well, what's that equal to? I just carry the denominator over here. That's going to be equal to the probability of A given Fj times the probability of Fj. So all I did is I take this equation here, and I cleared denominators by moving this guy over there. Now, having done this, I can now take this term here, which derives from our second equation, which we'll call 2, and I can substitute it here into the first equation. So I take this thing here, and I just substitute equals for equals into here, because this is the probability Fj intersect A. I've just solved for that. I can plug it in like this. So substituting our last equation 3 into 1, I can now simplify and write like this. The probability of Fj given A is equal to, let's just actually write it out, the probability of Fj intersect A over the probability of A. After our substitution, this is equal to the probability of A given Fj times the probability of Fj, that's J, over the probability of A. And we're done. So just a little algebra to prove this. So Bayes' formula, Bayes' theorem, follows directly from just the definition of conditional probability and a little bit of algebra. Now, that's a fair bit of formalism in a sense, though, but I just want to write one corollary And the corollary is extremely useful for calculation. Now, if you were asked to apply this in some problem, the thing you would run into right away is that you have various things you can calculate, but what is this beast here, the probability of A? How can we actually calculate that in some kind of way? And this is where the law of total probability comes in. So the law of total probability tells us that we can calculate the probability of A using this sum. So I'm just going to apply this theorem to substitute the expansion from the law of total probability here like this. So the corollary is let F1 up to Fn be pairwise disjoint, and let us assume that their union of all the Fi equals the entire outcome space, just like we already have. Then the probability of Fj given A, just this thing here, is equal to the same numerator, probability of A given Fj times the probability of Fj. And now the only thing I'm doing here is I'm taking the A and I'm expanding it using the law of total probability. So I have a P of A, probability of A in the denominator. I'm just expanding it out like this. So let me just substitute that in. Here we have the sum for I equals 1 to n of the probability of A given Fi times the probability of Fi. And this is going to make it substantially easier to calculate. So all we did is we took Bayes' formula, which is here, and we also proved it. And all we did is we replaced P of A in the denominator with the sum from the law of total probability. So very useful for calculating, and of course this is the basis, as I'll show you, for statistical inference. Now we have Bayes' theorem, and we've even proved it. But how about it like this? It's always good to have an example and figure out what's really going on by looking at some specific things. So I'm going to go back to our XKCD cartoon and do it in some more detail. All right. All right, so here's the scenario again. Now, I want to frame this a little bit. So a little probability statistics culture here is that this indicates different perspectives on statistics by statisticians who are frequentists and statisticians who are Bayesians. And the emphasis in this class should be on computing the Bayesian probability, because that's this lecture. I don't really want to understand for you the frequentist argument or get into a religious debate over frequentist versus Bayesian. But let's look at the cartoon a little bit, try to parse it. Now, how funny this is will be left as an exercise for the reader. We're not going to make you laugh or measure your laugh to get credit for this, but let me parse it. So two people here. One makes a neutrino detector. It's supposed to measure when the sun has gone nova. So basically what it does is it measures whether there's a swarm of neutrinos from the sun. Basically, it measures this and then it rolls 2 dice. So there either is a swarm or there isn't a swarm. It rolls 2 dice. If they both are 6s, it lies. Otherwise, it tells the truth. So they try it. And you ask the machine, has the sun gone nova, supernova? So the idea of this is that the frequentist statistician basically is going to look at this and isn't going to be able to model, or isn't going to want to model, the probability that the sun has gone nova, namely a neutrino storm. And it's basically going to conclude that the probability of rolling double 6s is about 2.7%, which is very small. So probably the machine didn't lie, because that's less than 0.05. Whereas the Bayesian statistician is going to use the prior probability that the sun has gone nova, which is very small, and says waggishly, I bet you it hasn't. Nevertheless, to actually investigate this in some sense, we need to understand 2 things. First, if you're confused about this, you can treat it as a black box. As I mentioned, when a star goes supernova or nova, it releases a swarm of neutrinos. Again, the physical basis for this can be seen from the Feynman diagram. Namely, this is traditional beta decay. basically in beta decay, the situation we have is that we have a neutron which decays into a proton, an electron, and an antineutrino. But physics is reversible, and under massive temperatures and pressures, things can go the other way. This is called neutronification, and a proton and an electron can combine to make a neutral particle called a neutron, and that releases a neutrino in the other direction. And this happens at a massive scale when a star collapses, or we have a sun going nova. For more on this, you might very much like to take a physics class. I recommend it highly. But let's look at what's going on here. Whenever I'm looking at a joke and trying to understand it, what I do is I write some code. So here's the code that I wrote. I know I put this up last time, but let's look into it a little bit more. So again, this is based on a version of Desmarais' game where he rolled 2 6s until he got double 6s and then bet money. So we have this here, and of course, we're coding it up at the bottom. So our machine calls a predicate neutrino storm. Basically, that's attached to the physical world. It measures whether or not there's a large number of neutrinos released, which returns a Boolean, the exploded. Then no matter what happens, the machine always rolls 2 dice. And if they're double 6s, it lies by inverting this Boolean, otherwise it tells the truth. So this is really what happens here. So the basic line here in the cartoon is that, and now you can see it because we have code. Code is always the way to understand something. So if we don't model the probability of a neutrino storm, we then are a frequentist, and we basically are concluding that the probability of this and clause is 1/36, or about 2.7%. Since that could be treated as being small, we might conclude that even if the machine says yes, that doesn't lie, and the sun has actually exploded. Whereas if we model that the probability of the neutrino storm is actually low, we come up with a different answer. And I'm going to calculate that for you now using Bayesian probability. So what's our goal here in terms of computer science instead of physics? So far in this class, we have developed a semantics for programs without randomization. In other words, there are no calls to the random function or any other source of randomness in there. What about with randomization? Many useful programs use randomization. There are entire courses on this. There are graduate students who are TAs for this class, who advisors specialize in this area. So we would like to be able to extend our model, say substitution model, to deal with randomness in some fashion. That's beyond the scope of this course, but I can give you some hints on how it might be done. So in short, we want to model the probability that the sun has gone nova and the probability of the dice rolling somehow in order to determine if the machine actually says yes, what's the probability that in reality the sun has exploded? It's dark, so we don't know. We only have the machine. And Bayesian probability to the rescue. So the short answer for this is that in the joke, the Bayesian statistician knows that the probability of the sun going nova at any instant is very small. Let us call it epsilon. And that makes the claim, the chance that the machine rolled double 6s, a near certainty if it says that the sun has exploded. But let's try to calculate this. And the great thing about our statistical framework now is that we can do this inference just using what we've already learned today. So let me do the calculation for you. Now, you may not know this, but I think it's a pretty funny joke. And so do a lot of mathematicians. You don't have to think it's funny. But my undergraduate degree is actually in literature, Russian literature, particularly poetry. And one of the things that I was taught as an undergraduate is that in order to understand why something is beautiful or funny, we need to pull all the petals off it and dissect it. And that actually is the basis of molecular biology as well, which is my current field. So here we're going to dissect this using formulas for Bayesian statistics. And then at the end, we'll really understand mathematically the extent to which this is actually funny. So let's think about this. So I have this sort of informal claim about what the frequentist or Bayesian might do, but let's try to write this down. So let's have some events. F1, this is the event that we'll call the sun has gone nova, right? And the probability of this is small. So the probability of it going nova, which I'll just write as the probability of F1, is epsilon, which is very close to 0, but maybe not exactly equal to 0. There we go. Now, F2 is its complement. F2 is basically the state of not going nova. So the sun is not exploded. And the probability of F2, and of course we can write F2 as, the complement of F1, because just like before, it's going to take up the entire outcome space. Probably F2 is equal to 1 minus epsilon, which is very close to 1, but not equal to 1. Okay. And then the third event we have to think about is our arbitrary event A in this case, which is that the machine says yes in the cartoon. Obviously, in our code, the machine says true instead. So these are the events that we're interested in. Now you can, I hope, see the beauty from this next equation. We're interested in the probability of F1 given A. Why are we interested in this? So A is what we observed. A is what the machine tells us, right? The machine says yes. But we're interested in that if it says yes, what is the real probability under the Bayesian framework that the sun is actually exploded? So that's why this is of a lot of interest. So we can compute this using Bayes' law with the law of total probability in the denominator, and we'll just write that out. So at the end, we have this formula here. We go back to Bayes' law. We're going to look up Bayes' formula. We're going to expand the denominator to have the summation there, and then we're going to calculate. It's not a difficult calculation. So this is, of course, just using the formula, the probability of A given F1 times the probability of F1. And down here, we have the probability of A, namely the probability of A given F1 times the probability of F1 plus the probability of A given F2 times the probability of F2. And just not to put too fine a point on it, I just want to mention that this is the probability of A, and we know that by the law of total probability. And we know this from Bayes' theorem. So we're just using the theorem here. Okay, so we have this formula. How do we calculate? Well, let's start putting in some numbers. So some of these are pretty easy. So I'd like to compute first the probability of A given F1. Why? Because it's the first term here. So here, let's look at the code again. I think that will be instructive and see what's going on. So the probability of A given F1, now this can be computed by setting exploded to true and calculating probabilities. And in that sense, you can think of this as an extension of the substitution model to calculate conditional probabilities. So it's very much tied in with understanding what programs are based on probabilities. So probably A given F1, and this is, probably the machine says yes, given that the sun has gone nova. This is simply equal to 35 out of 36. Let me just annotate this. The probability of the machine says yes, given that the sun is actually exploded. On the other hand, the probability of A given F2 is equal to 1 over 36. This is the probability that the machine says yes, and the sun has not exploded. Okay, so armed with these two probabilities, which come directly from our combinatorial probability analysis of dice, we can now expand this. I'm going to take this equation here, and I'm just going to substitute in these probabilities and calculate. So this probability is equal to 35 over 36 times epsilon over 35 over 36 times epsilon plus 1 over 36 times 1 minus epsilon. Well, what the heck is epsilon? So I don't know, but it's pretty small. So let's say, just to do some calculations, let's take epsilon to be 1 part in a billion. Just to calculate, I'm just saying, suppose the probability of the sun going nova at any instant is only 1 in a billion. So very unlikely. Then this expands out to 35 over 10 to the 9th plus 34, which is pretty close to 0. And that's why in the cartoon, see, the frequentist is only looking at the dice roll, right? They're saying, well, it's pretty unlikely it lied. The Bayesian's saying, I actually did the calculation. I don't think the sun exploded. I'll bet you $50 it hasn't. So that's why that's why probabilists and statisticians find this amusing. Okay. So you've been very patient. I'm going to allude to a conversation happening in the field. So at most universities, you have statisticians who are frequentists, namely they are doing calculations that are parodied here, or they're Bayesians. There are usually a few of those. At Duke, they're overwhelmingly Bayesian, which is useful because if you're an AI machine learning person, Bayesian statistics is incredibly useful for bootstrapping statistical inference and machine learning. But basically, the frequentist viewpoint is somewhat deprecated here. Other places, the frequentists are more powerful in some sense. I don't want to wade into this conversation. I'll let you make your own decisions. You can choose your own theories, but you should know that there's a kind of a discussion in the field about which approach is more fruitful. But Bayesian calculation is very useful, and that's what we're studying in this lecture. And we've now done a calculation based on the cartoon. All right, so let's go back to what we can say from the computer science, not the probability point of view about this. Go back to our code here. So consider our program called machine, which I've drawn here. So using our Bayesian framework, as you've seen, we can now develop a semantics for predicting and understanding when these programs return an answer like true or false, even with randomness. So the issue here is a probabilistic semantics versus deterministic semantics. That's kind of the key thing that we're trying to get at here. Okay. All right. So this is not something we'll develop in this class, but it's something that I'll allude to here. And really what I'd like you to take away from this is a foundation in conditional probability, which will be very useful for problem set 6, and some understanding of the Bayesian calculations, Bayes formula, because they're very useful in many places. The idea of developing something as powerful as the substitution model that would apply to programs with randomness is for a later class, but I think that you can see that we have the foundations for beginning to think about it. We won't ask you about that, but you might want to take a class about that in the future. All right. So I have more stuff I'd like to do, but I'd like to pause and ask if there are any questions or if I can clarify anything or any discussion. How many of you had seen Bayes' theorem before? A few? Had you proved it before, or had it just been stated and you used it? Emma says no proof. Yeah, so this is interesting. I mean, this is probably the easiest proof we do in this class, and also would be the easiest proof in a statistics class. So I think it's definitely worth proving at least the things that are easy to prove, so you can know that it's actually true. All right, any questions on our calculations or what we've done today?
So could you just clarify what epsilon and then the output of the formula actually represents?
Sure, absolutely. Let's do that. So in order to do Bayesian statistics or Bayesian inference, I need to have a prior probability estimate for some of these events, right? And I'm using some intuition about physics to estimate that the probability of the sun going nova at any instant, or even in any day, is rather small. So that's my goal. But I can't really put those words into a mathematical calculation without assigning numbers to them. So what I did is I just said, well, let's make it, the probability is arbitrary, I call it epsilon, but I'll hint to you that it's close to 0. because I kind of want to do some calculations. And then of course 1 minus epsilon is close to 1. So this just says it's some small constant.
Okay, and epsilon would represent like the expected probability then, or?
No, it's actually the probability.
Okay.
It's not expected, it's just actual. I'm just estimating the probability of the sun going nova to be something small. So this is sort of the main trick between in Bayesian inference, is that you're computing probabilities, but for some of these events, you have prior knowledge of what the probabilities of individual events might be, and then you're combining them. So this is an example of how we can apply sort of rigorous mathematics, namely the combinatorial calculations about die, right? As a fair die, that's actually mathematically exactly right, with any prior knowledge that we might have. So if we have prior knowledge that a supernova is a rare event, we can incorporate that into this framework.
Right, and that's where I'm a little bit confused. So if we have prior knowledge of what the probability of the sun exploding here is, what does the formula calculate exactly? I'm a little just like confused.
Absolutely. So this is the probability of F1 given A. So we're in a situation. So it's not. So we have this device here, and so we run the machine, and it says yes. Namely, it says the sun is. So you ask the machine, has the sun exploded, and the machine says yes. So the question here is, did the sun really explode?
Oh, okay. What are the odds that the sun exploded given the output of the?
Right.
Okay.
And it's always good. I mean, I always good to check someone here. Whenever you see someone doing a derivation like this, go back to the definitions of the events. So again, F1 if the event is nova, so P of F1 is the probability of going nova. A is the event the machine says yes. So P of F1 given A is the probability of the event the sun has gone nova, given that the machine said yes. And we know what the machine did.
Okay. Yeah. Thanks so much.
Yeah, no, great question. It is subtle for sure. And then down here, I just did a calculation with a small one. Yeah, terrific discussion. Any more comments or questions? All right, what I'd like to do now is, of course, you can always ask me questions later. What I'd like to do now is go back to our law of total probability and see if we can prove this. So we've been using it. We used it last time, we used it this time. So how do we actually know that something like this is true? Now, how do we go about proving a thing like this? So I think we have time to ask you all how you prove it, and to break out for a little bit and then come back. So we're doing really quite good on time. So feel free to take a screenshot, although this is also included in lecture from last time, because I think during breakout rooms you cannot see, you can't see the screen. I'll assign you your breakout rooms for about, well, maybe let's say 7 minutes. Try to use what you've proven. You definitely have the ability to do that. And I'll bring you back and I'll ask you, hey, how you doing? And I'll give you hints to how to solve it. Because this is a very useful